Sir, audible, sir.
Yes, what we have discussed in the previous classes.
Rasa.
So about
Answer.
deletion. So deletion.
So in the binary
About
search,
deletion.
in a binary search tree, we have been doing some of an operation in a binary search tree. We have completed those all the operations. So one is going to be an insert, search, traversal, finding the minimum and maximum, and delete. So these are the operations in a binary search tree. So now we will move with the next topic, which will be consist of AVL trees. So AVL trees is the advanced of a binary search tree. So can anyone tell me what is the major property of binary search tree? What is the properties of binary search tree?
It
If
has
it is a binary
exactly
search tree,
zero
how
or
you
two
will?
child.
Yes,
Exactly zero or two child, sir, for parent node.
exactly zero or two child. Apart from that, one more properties is there. The tree.
So highest values in right side or lowest values in right.
Yes, yes. So yes, the highest value in the right side, and the smallest value of the root node will be in the left hand side. So this will be the two properties that we are following in a binary search tree. So while this continuation of this, in this AVL tree, what we have done, we before going to the AVL tree, we have studied this, right? Balanced binary tree, but we have not used this balanced binary tree in your operations, right? Have you remember this? In the tree type, tree types, we have studied one balanced binary tree. Have you remember this?
Yes, sir.
Yes, sir.
Yes, but this process we have not used in a binary tree, and we have not checked in the binary tree with this formula. For this is known as the AVL tree. So this is also known as the AVL tree. Once you have structured the binary tree, and after structuring the binary tree, we want to find out whether that is the balanced binary tree. How you find out the balanced binary tree? You want to go to all the nodes and you want to find whether the left hand side minus right hand side is equal to the value want to be in 0, 1 or minus 1. If it is more than minus 1 or more than 1, then that is not a balanced binary tree. For overcoming this concept, we are going with this concept called AVL tree. Are you clear about this? Before the why we are going for AVL tree when you are having the binary search tree, why we are going for the AVL tree? Okay, I will tell you that. An AVL tree is a self-balancing binary tree. So self-balancing binary tree. It is also known as the self-balance. That is a balanced binary tree. It means that self-balancing binary tree. So in your exam point of view, if they are asking a self-balancing binary tree, you want to write an algorithm for an AVL tree, how the binary tree will be sorted in your program. And after sorting, you want to check whether that is balanced or not. If it is not balanced, we want to apply this AVL method in your program or algorithm. That is the thing. It is also satisfied the properties of binary tree. It means the properties which will be consist of the child wants to be either 0, 1 or 2. That is the first property of binary search tree. And apart from that, the lower value in the left hand side, highest value in the right hand side. So these two properties want to be satisfied first. So it was the first such data structure to be invented. This is the first thing we have invented to find out the balanced binary tree. In this AVL tree, the height of two subtrees of any node differ by the most of one. If any time they differ more than one, that at that time this AVL tree will not be satisfied. Then we want to go for an alteration of that particular tree. If it is more than one, the self-balancing factor is more than one, then we want to go to the alteration method and we want to alter the binary tree with the satisfied of this binary search method. You want to satisfy this binary search method as well as you want to alter the that which was not satisfied. So rebalancing is done to store this property. So that is known as rebalancing. So rebalancing want to be done. That rebalancing, how you want to be done, we will discuss in the upcoming slide. So this is invented by Adelson, Welski, and Lendas. Welski and Lendas. So these are all the invented peoples. Adelson, Welski, and Lendas. So that is then AVL. So that is an abbreviation of AVL. So this was developed for reducing your time. Binary tree also is a reducing of time, and this self-balancing binary tree which reduce the more time when compared to the binary search tree. For that, if you are having a number of nodes in your, when I am going with an example, then I will tell you that So balancing the height of left subtree and a right subtree, that is a major concept. So we want to balance those height in a left subtree as well as the right subtree. So measuring in the term of balancing factor. So the balancing factor will be 0, 1 or -1. So that I have just explained in the second class of the fourth unit. I will explain you fully now. So how we want to find out the balancing factor, that is height of left subtree minus height of right subtree. This want to be mentioned for every node, not only one node. We want to start from the leaf node to the root node. For each and every node, we want to find out this balancing factor, that is height of left subtree minus height of right subtree. If the balancing factor, any one of the node, the balancing factor is not satisfied, then you want to stop there and you want to do a rotation method over there, and you want to structure the self-balancing binary tree. It means the longest path from the leaf node to the particular node. You want to find out the longest path from the leaf node to that particular node. What you are going to discuss, what you are going to find out, whether that is the height of the, you are going to find any one of the balancing factor for the particular node. And that time you want to find out that you want to start from the leaf node. That is only one condition with the AVL tree. So that's balancing factor. If after finding out this, if any one of the node is getting 1 as the balancing factor, then thus that tree will known as the heavy right AVL tree. That if you are getting 1 as the balancing factor, then that tree is known as the heavy right AVL tree. If you are getting 0 of the root node, then the balancing factor will be balancing AVL tree. If you are getting -1, it means that heavy left AVL tree. So that we, after the example, if you are coming with this 3 points, then you can able to understand easily. If it is not satisfied the factor, then it is known as the imbalancing tree. If it is not satisfied of these 3 things, the root node is not satisfied of these 3 things, then that is known as the imbalancing tree. Then you want to go with some of an operations called rotation. That is, there is 4 types of rotation you can able to do. That is LL rotation, RR rotation, LR rotation, and RL rotation. So LL rotation is an inserting node of left subtree. So first you will go with an example, then you can go with this. So here you can see, on the screen is visible, right? Yes. Here you can see here, this is my root node. So this is my tree. Whether it is a binary tree, first you want to check whether it is satisfied the binary tree or not. Whether it is a binary tree. So all the node is having either 0 child, 1 child, or 2 child, right? Yes.
0 or 2 child.
Binary tree.
Yes.
Sir, value 30 and 40.
Okay.
Seven.
So make this as 50. If it is right.
Yes, sir.
Yes. So first you want to satisfy the condition of the binary tree, and after that we want to find out the balancing factor of each and individual node. That means we want to check from the root node. So what is the balancing factor formula? What is the balancing factor formula? That height of left subtree minus height of right subtree. So that is the balancing factor formula. For every node, you want to find out the balancing factor formula for every node. So for this 60, what is the height of left subtree? For this 60.
0.
So 0. So there is no left tree. So it will be 0 minus 0. So it will be 0. So it has been satisfied. For this 40, it is 0 minus 0. It is 0. So it has been satisfied. So for this 100, it is 0 minus 0. It is 0. So this also is satisfied. For this 50, the height of left subtree will be 1 and height of left subtree will be 1. So 1 minus 0, it will be 0. So it will be in a balancing factor. And for this 80, the left subtree is 1 and 2, right? 2 and the right subtree will be 1. So 2 minus 1 is equal to 1. So this is a complete binary. This is a self-balancing binary tree. So no need to do any operation between the AVL process. You no need to rotate anything. So as like that, this process is known as the self-balancing binary tree. Clear about this?
Yes, sir.
Yes, sir.
Yes. Now coming to the second one. So now you can see here. So first you have, so this is the binary tree I have got for the particular data. This is my binary tree I have got. So here I am checking for this 45, 0 minus 0, that will be 0. So this is satisfied. So this is satisfied. And 40, 1 minus 1. So it will be satisfied. For 60, this is a leaf node. So 0 minus 0 is 0. And this is also a leaf node. 0 minus 0 is equal to 0. For this 50, left subtree will be 2 and right subtree will be 1. 2 minus 1. So it will be satisfied. And here you can come. For this 80, that is root node, left subtree will be 1, 2, and 3. And right subtree will be 2, 1. So it means 3 minus 1. So here the collusion impossible binary tree has been occurred. So AVL tree has been occurred. So for this kind of statement, we want to do that operation what I have mentioned here. For this kind of tree that you are getting after the binary tree, to make this as a complete binary tree, then you want to do this operation, that is LL rotation, RR rotation, LR rotation, and RL rotation. So I will explain. So have you clear about this two things, right? How the AVL binary tree will be and how the AVL will not satisfy this condition. So these two you have understand, right?
Yes, sir.
Yes. Yes. So now we will move with the LL rotation. You just consider this is my LL is the sense inserting node of left subtree. That is the concept. Inserting node of left subtree. Inserting a node of left subtree. So now I will tell you this. So now you can tell me what is the balancing factor of the C.
0.
Balancing factor 0 minus 0, so it will be 0, right? And balancing factor of B,
1.
1.
height of left subtree minus height of right subtree. Height of left subtree will be 1 and height of right subtree will be 0. So 1 minus 0, it will be 1. So what is the balancing factor of A?
2.
2 minus 1.
2 minus
2 minus 0.
0.
2 minus 0. 2 minus 0, it will be 2. So now you can see here where the collusion has been occurred. So here the collusion has been occurred. If your tree structure will be like this, inserting node of left subtree. So when this collusion has been occurred, while inserting this C over here, this collusion has been occurred, right? Inserting node of left subtree. For this, we want to do a rotation that is called as LL rotation. We want to do here for making this as a balanced binary tree. So for this, I am rotating the statement. So I am rotating this tree in the right hand side. So it will be rotating this tree in the right hand side. And after rotating, the value will be like this. B, C, and A. So this is the rotation technique. So while you are going with the numbers also, it will be working. When you are going with the numbers also, it will be work. So that we will discuss in an example. So likewise, it will be changed. So it will be rotate in a right hand side. So it is a left subtree. So it will be rotate in a right hand side to make this as a balanced binary tree. So now you can check this for the root. What is the balancing factor of A?
0,
0,
0. Balancing factor of C?
0,
0,
0. Balancing factor of B?
0, sir.
0. So this is the, it was satisfying the condition, so it is a self-balancing binary tree. So that is the concept. Have you understand this? When you are inserting, when you are having the element in the left side of left node that was left of left subtree, when you are inserting the 6, the collision will be, when inserting the C, the collision will be happened in A. So if you are eliminating the C, if you are searching this 2 tree, you are checking the balance factor, then it will be satisfied. Once the node, this node has been inserted, then you want to switch and rotate this thing in a right hand side to get this particular result. So that is the concept. When you are going with an example, then you can able to understand. Now we will move with RR. So it means RR means inserting node of right subtree. Inserting node of right subtree. So inserting a node of right subtree. This is when you are inserting the C, the collision will be happen. Let's see how it will be done. So what is the balancing factor of C?
0,
0,
0. What is the balancing factor of B?
1,
minus 1,
Minus 1. And what is the balancing factor of A?
minus 2,
minus 2,
Minus 2. So here you can see, here the imbalance factor has been occurred. It means that it was inserting a right subtree. When you are inserting the C, the balancing factor has been occurred. So we want to rotate this is in the left hand side. We want to rotate this in the left hand side. Now how will the tree will be? What is my root node now?
B,
So B is my root node, A will be coming here and C will be coming. So now you can check the balancing factor of this. This will be 0, this will be 0, and this will be 0. Clear? Clear about this? Any doubts in this tool rotation? So when you are going with an example, I will tell you how it will be work. This is a concept of this rotation. How you want to rotate. If your tree is like this, then you want to rotate in a right subtree. When your tree like in the left hand side process, you want to rotate in the right subtree. So right hand side, that is the concept, tool concept. And now coming to the LR rotation. So what is meant by LR? Inserting node of right of left subtree. Inserting a node of right of left subtree. So now you can see inserting a node of right of left subtree. So that is the process. So this is a two-step process. So when you are having the process in the adjacent side, then it will be a single step. If you are having in the adjacent side, then this will be the two-step process. So first step, what we want to done. So this want to be rotate in a left hand side. Only this C want to be rotate in the left hand side. So it means how it will be coming over here. So first step, how it will be A, B, sorry, A, C, and B. This is the step. So now you can find out the impact factor here. So what is the impact factor of C? That will be 0. So for B, 0 minus 1, it will be minus 1. For C, 1, 2, 1 and 2. 2 minus 0, that will be 2. So here the balancing imbalance factor has been occurred. So it means it will be consist of two steps. So one is, first we want to go with these two nodes. First we want to go with these two nodes and we want to interchange with the rotation of right. So like for first step like this, the structure will be happen. So it is for this structure we already discussed, that is an LL rotation. So after that we want to insert that LL rotation here. So after rotation this, so this is my first step. This is my first step. And in the second step, the LL notation will be considered. And after considering the LL notation, what is my root node now?
C.
What is my root node?
So not audible, sir.
Am I audible now?
Yes, sir.
So this is my two-step process. The process which will be consist of two-step process for LR notation. First we want to make this adjacent side, and after that we want to apply for the LL notations. So this is the two-step. And now coming to the RL notation, same the thing that will be inserted in the right-hand side. For what is an RL notation? Inserting node or of left of right subtree. Inserting a node of left of right subtree. Inserting a node of left of right subtree. Inserting a node in a left of right subtree. So now this will be also considered as a two-step process. So what is the impact factor of the C? To C it will be 0, right? And what is B?
1.
Minus
1.
1.
And what is A?
Minus 2.
Minus 2.
Minus 2. So here the
B
imbalance
minus
factor is B minus 1. So B is 1. So height of left subtree minus right subtree. Here left subtree will be 1 and right subtree is 0. So 1 minus 0 it will be 0. So here height of left subtree is 0 and right subtree is 2. So 0 minus 2 it will be 2. So here the imbalance factor has been occurred. So we want to do this RL. So inserting a node in a left of right subtree. When you are inserting this C only, this collision has been happened. So it means inserting a node of left of right subtree. So two-step process want to be occur. So first step we want to rotate this in a right. So here it will be consist of A, C, and D. A, C, and D. So this is the first step when you are rotating the C over here. So this is known as the RR operation. This is known as the RR rotation. So this structure is known as the RR rotation. So while doing this RR notation, again you want to go, no need of checking those things, because this is a two-step process. After completion of the second step, we can check the balancing factor. So now what will happen? It will rotate in the right hand side, right? Left hand side, right? So the C will be your root node, and A will be your left subtree, and B will be your right sub. So now you are checking the imbalance factor. It will be 0, it will be 0, and it will be 0. So the condition has been checked, and it was an AVL tree. So it is a binary tree and also an AVL tree. So likewise, we want to interchange, or you want to do the process to bring your binary tree as an AVL tree while using those formula. The height of left subtree minus height of right subtree, the impact factor want to be either -1, 0, or 1. If you are moving like 2, 3, 4, then you want to do this rotation operation and you want to perform the AVL tree process in your program. Understand?
Yes, sir.
Let me move with an example. Yes. Let me move with an example.
Yes, sir.
Yes.
Yes, sir.
So this is an example. So here, till now we have discussed only with the character called A, B, and C. So now we will move the real-time example of a binary tree. So binary search tree, how this will be occur with the satisfaction of a condition of AVL tree. So now we will move the step-by-step process. So first step, what will be the insertion of this node? First node will be inserted.
Root node 20.
20. So first step, the root node will be inserted. And now coming to the second step, what will be the insertion?
Right side 30.
20. In the right side of the node, it will be 30. 20. So now we can check the impact factor, balancing factor for this 20. For this 30, the balancing factor is
0.
0. For this,
-1.
-1. So in this case, it was condition as checked for AVL tree. So it is a binary search tree as well as the AVL tree. So the condition has been checked. And now third point.
For 30, right side 80, sir.
So 20, 30, and 80. So now you can check the balancing factor here. It is 80. For 80, it will be 0. For 30, it will be -1.
-1.
For 20, -2.
-2.
So while inserting this, the imbalancing, for inserting this 80, the imbalancing factor has been appeared, right? Yes.
Yes, sir.
Which rotation we want to do now?
RR.
RR notation we want to do now. So it means the output which will be consist of 30,
20 and 80.
20, 80.
20, 80. Whether it is satisfied the binary search tree,
Yes, sir.
whether it is satisfied the binary search tree properties. Yes. So it is the root node left hand side will be smaller and root node right hand side will be larger. So it is satisfied of binary search tree. So in this third step, we have do that RR step to convert that as an AVL tree. So now you can see this. It will be 0, it will be 0, and it will be 0. Are you clear about this?
Yes, sir.
Yes. The fourth step.
For 80, left side 40, sir.
So in the fourth step, what will happen?
80, left
30.
side
So
40.
before that 30, 20,
20,
and
80,
80. And now you are going to
80
insert
left
the
side
80 left side will be 40.
40.
Right? Yes. So now you can check the balancing factor. For this 40 0. For this
1
1. This
-2 -1
now
0,
minus
sir.
1.
-1.
Minus 1. The left side, the height of left subtree is 1 and height of right subtree is 2. So 1 minus 2 it will be consist of -1. For this 0, the 20, it will be 0, right?
Yes, sir.
So this satisfied. This for when you are inserting this 40, it will be satisfied. Now you can go with the fifth step. 30, 20, 80, 40. What is the next value now?
20
10
left, 10, sir.
20 left, it will be 10. So now you can find out the balancing factor. It will be 0. The leaf node will be 0. For this 80, it will
1.
be 1.
1,
1
For this 20, it will be 1.
1
1,
For this 30,
0.
0
0. So this also will be satisfied. Now coming to not satisfying. So coming to the sixth one.
30, 20,
30, 20,
10.
80, 10,
Left 40, right 60, sir.
40.
80, right 60.
How it will come 80 right 60?
40 sir. 40 right 60
40 right, it will be 60. You want to insert the greater number in the right hand side, right?
Yes,
80
sir.
is not greater than 60. So 80 is not less than 60. So you want to insert this 40. So now you can see this impact factor of the 60. What is the impact factor of 60?
0
0 here for 40,
-1
-1. For here 0, 10 it will be 0. And for 80,
2 sir.
so 2 minus 0, it will be 2. So if you are getting any imbalance factor in the mid of the node, then no need to check the remaining node. So first you want to clear this and you want to check the remaining node. So first you want to do, this is a two-step operation. This is known as the, what it is?
LR
LR, inserting node of right of left subtree. So that is an LR operation. You want to do here inserting node as right in a left subtree. So you want to do an LR operation. So LR operation, you know that LR operation is the two-step operation, right?
yes sir.
Yes, yes. So we want to insert, first we want to insert the third 30, 20, 80, 10, and this 80 will not come here. So what is the two-step after finalizing? What is the first step here? So this 60 will be moved here. So 80, 60, and 40. This is my first step. Am I right? So this
Yes
60
sir.
will be moved here. So again, here in the right rotation will be happen. So it means 60, 80, and 40. Whether it is satisfied the binary search tree?
Yes sir.
Yes, it was satisfied because the node left hand side will be smaller and right hand side will be larger. So it is satisfied the binary search tree. So now you can find out the balancing factor. For this 80 will be 0, 40 will be 0, 10 will be 0. What about 60? It will be 0, right? Height of left subtree minus right subtree, it will be 0. So here for 20, height of left subtree minus height of right subtree, it will be 1, right?
Yes sir.
So this 30, height of left subtree minus height of right
2
subtree. Height of left
-2
subtree is 2 and height of right subtree will be 2. So it will be 0. So now what is happened is, this is satisfied the AVL tree concept. Are you getting this?
Yes, sir.
Yes. So the remaining nodes will be 50 and 60. So it will be so the remaining node will be 50 and 60. So
70,
the
70, sir.
50 and 70. The remaining node will be 50 and 70. So final structure of this node will be like this, I hope so. So it will be 30, 20, 60, 10, 40, 80. 30, 20, 60, 10, 40, and 80. So now coming to the 7th step, what I want to insert here? 50 I want to insert.
50.
Where I want to insert this 50?
Right side of 40, sir.
Yes, right side of 40, I want to insert this 50. So now we can check the balancing factor of all the nodes. So for 50 it will be 0, for 80 it will be 0, and what about 40?
-1.
Minus 1. What about 60?
1.
1. And what about 20?
1.
1. 10 it will be 0. And now you can see here for 30.
-1.
So height of left subtree is 2, height of right subtree is 1, 2, and 3. So 2 minus 3, it will be -1. So in this condition, it will satisfy the AVL tree concept. So when you are inserting the next element, 30, 20, 60, 10, 40, 80, 50. So where I want to insert the 70?
Left side of 80, sir.
Left of 80.
So left side of 80, I want to insert the 70. So now you can check the balancing factor. For 70, it will be 0, and 50, it will be 0, 10, it will be 0. For what is the balancing factor of 80?
1.
1. What is the balancing factor of 40?
minus
-1.
Minus 1. What is the balancing factor of 60?
0.
0. For 20?
1.
1.
1. For 30?
-1.
Minus 1. Yes. 2 minus 3, so it will be -1. So now it is also satisfied, all the node has been satisfied for AVL tree concept. So this is also known as, this is for final tree structure like this, if you are getting, it will be consist of AVL tree concept. So without consist of AVL tree concept, one minute, I will tell you this. By using the AVL tree, we have finally got those things like this. And you just imagine if you are not using the this AVL tree, how the output will be. If you are not using the AVL tree, you are just using a binary search tree. What is my first node now?
20.
20.
Left to 10, sir.
No, we will go through node by node. 30. And where the 80 will be? 80 will be here, right?
Right.
And
40.
the 40 will be in the left. And
For
10 will,
20,
10 will be left of 20.
and where the 60?
40 right.
40 right.
And where the 50?
60 left.
60 left, it will be 50. And where the 70?
60 right.
Right.
60 right, it will be 70. So without using the AVL tree, you can see here how the tree structure will be. Yes? Can you see, feel the difference for this when you are using the AVL tree? This
Yes,
is the structure by using the AVL tree. So binary tree is the simple method of searching technique. But apart from the binary tree, we having an advanced tree that is known as an AVL tree. If suppose I want to search an element called 70, am I right? You just imagine that if suppose I want to search an element called 70 in a binary search tree, It will travels 1, 2, 3, 4, 5, and the sixth node you will get an output. Now coming here, if I need to search an element called 70, 1, 2, third node, I will get an output here. Are you clear about this?
Yes, sir.
Yes. So simplifying your searching methodology, again we are going to one of the tree that is known as an AVL tree. So that is the thing. So in your subject oriented, in your syllabus, there is no program for this AVL tree. They are not given any program in your textbook. They are given only a syntax for this AVL tree and an operation how it will be working over here. So if time has been permit, I will go with an AVL tree program also. So it will be consist of huge number of codes for AVL tree. You want to check when you are inserting each and every node inside the tree, you want to check whether that is an AVL tree or not. So it will be a huge number of lines of code. When the time permits, I will explain you this AVL tree lines of code in detail, right? So I hope so. It will be permits after completion of the 4th unit. If it is permits, then I will be explaining you that. And the basic operation, if you are asking in your exam point of view, the basic operation will be this. That is the balancing factor you want to know, and the rotation, how the rotation will be done. You want to take an example of this rotation, and the rotation want to be done. And now what we have seen is the inserting method we have seen. That is an operation. That is an operation we have seen. And the deletion method, same as like that, how we were deleting a node in a binary search tree, how we will delete the binary search tree. What is the step for deleting a binary search tree? We are having a 3 type, that is a single node, 1 child node, and 2 child node, right?
Yes, sir.
Yes. So same method of deleting in an AVL tree. If you are deleting an AVL tree, this left child will be coming over here. Again, you want to check whether that is an AVL tree or not. If it is not an AVL tree, you want to rotate those things again. That is the concept. That is the concept of insertion and deletion. Insertion we have done here. We have inserting and each and individual node now. Insertion we have done. And the deletion is the thing. If I am deleting this 30, so okay, if I am deleting this 20 over 10 over here, I want to delete this 10. Whether this has, so maybe go with this example. If I am deleting this 10 over here, after deleting this, when you are finding out the factor of this AVL tree, whether it is satisfied,
No, sir.
no, it won't satisfy. So again, what we want to do, we want to rotate this left hand side towards the right hand side, right? So this 30 and 20 will be coming here, and 60 will be your root node. So likewise, it want to be changed. So that is the thing will be happen when your deleting process has been occurred. So when same thing, it will be to happen for the deleting process. Clear?
Yes.
Yes. So these are the things. So so when the 7th is your exam, right? Internal 2.
8th, sir.
8th. So this is your assignment 2.3 and 2.4. So first, the tree structure and list out all the terminologies and types of binary tree with an example, and write down the operation of BSTT and give the explanation with an example. That is the second assignment I have given. And third assignment, that 3.3 will be the explain the BST program using search, insert, delete, traversal, and create, search, traversal, delete, and search method. So what I have given, that is the thing I have given to you as an example. So take a different types of example and explain the program how it will be working. So that is a 3.3, and 3.4 will be the explain the AVL tree operation and rotation with an example. You can take any rotation. So that want to be considered, that want to be satisfied the binary tree as well as the AVL tree also. That you want to be in explain. So that is a 3.4. The submission date is not yet given to you. So take your time and do this work. So that is 4 exercises in the fourth unit. 3.1, 2, 3, and 4. Take the snapshot of this. You can take the snapshot of this. So there is, I have not given any submission date. After completion of the heap search, then I will give you the submission date for all the 5. Right? Any doubts? Any doubts? If you are not having any doubts, you can give your attendance and you can leave now.